Swayam Prabha. Digital India. Educated India.
Welcome back to the second lecture on the Muffler Acoustics course. So, we left at the following point. This was our equation, one dimensional acoustic wave propagation equation. And what we saw was that P tilde, which is your acoustic pressure as a function of space and time, is expressed in the following form, where F and G are general functions, continuous, twice differentiable, and they could be, like I said, sinusoidals, complex exponential, algebraic forms, anything which is a continuous function, at least twice differentiable. This term represents the forward propagating wave, this term represents the backward propagating wave or towards a negative x direction. So, in the last lecture we talked about deriving certain solutions for the equations when they are subjected to certain initial conditions. So, let us see how do we go about doing that. So, let us say you have a duct, and there is something like a pulse, some disturbance, maybe you can consider a membrane kind of a thing here, inflated membrane or something, and this goes in the infinity in the positive x direction and also towards the negative x direction, and it is a rigid wall duct. Only planar waves can propagate, that is wave fronts that propagate along this side and along this side. So, the idea is that when the membrane is completely ruptured, let me go to the next slide. Your duct system is here, and the membrane is ruptured now, it is completely, you put a pin or something and it produces a noise, tuck, something like that, and so it produces a wave, actually two waves, a pair of waves, one that propagates, like I said, in this direction and the other one in the negative x direction. Okay. So, the membrane is gone, there is disturbance which propagates. The reason that I am discussing about this particular problem or this situation, because this is again modeled by the wave propagation equation, and it has two waves, the one that goes towards the positive x direction, one that goes towards the negative x direction. And importantly, let us say just at the time t is equal to say 0, okay, P of x 0 is phi. General solution looks like phi x. Now, the time wise derivative, let us say that is 0, that means with respect to time this is 0. So, I will call this equation 1, equation 2, these are initial conditions, all right. So, the idea is that how to incorporate these initial conditions in the final solution. now that we know that we have solution given by this equation here, how do we enforce the initial condition given by 1 and 2 into the solution that I had shown. So, first of all we will substitute this. So, at t is equal to 0, what we saw is that f of x plus g of x is equal to phi x. That is simple, it follows by substituting t is equal to 0 in here, and what we get is this. So, p of x 0 is this thing. Now, what about the time derivative? The time derivative, if you recall the last lecture, we need to take the derivative with respect to the variable, that is here of course, it means with respect to time, but applying the chain rules we can go about evaluating the derivative. In any case, it works out in the following fashion. When we implement this, the second condition in this equation, what we see is that f dash at x minus c naught t evaluated at t is equal to 0 plus g dash of x plus c naught times t evaluated at t is equal to 0 is what? This was p, right. So, what we had done effectively, so this is 0 because we are enforcing this condition where I am pointing towards, right. So, when we do this, we really mean for that thing. So, we get minus C naught times something like this. So, basically going back to this equation, we figure out that this is minus C naught times f dash at t is 0. So, it is x plus, and here of course, there will be C naught. The students can derive this form, it is very simple. This thing is equal to 0. So, eventually what we get is that at C naught cancels out. So, we get something like f dash x minus so this is still with respect to that particular derivative. Now, if we integrate equation 3, what we get is minus f of x naught plus g of x naught is equal to some arbitrary constant of integration, which is say c. Okay. So, we will call this equation 4 and then go about doing some algebraic manipulations. Now, one thing is there, if you look at this equation where we got, maybe I should have numbered this is 2b suppose. So, when we combine 2b and equation number 4, what do we get? We have these conditions f of x plus g of x is equal to phi of x, is understood, and minus f of x plus g of x is equal to c. Now, we just need to add these two things and simplify to get the following. and then when you subtract say this equation from this one, what we get is the following: g of x and f of x. So, we have got our functions. So, let us call this equation 5a, 5b. So, now this is right for the time t naught, that is say t is equal to 0, t is equal to t naught. So, the total solution or the complete solution at this thing will be what? Phi of x by t like this. But now we have to find out a solution for a generic time t. So, what do? We need to translate this thing in terms of x minus c naught, and this one will be x plus c naught. So, for a generic time t, we will get things like this. Now, these two terms will cancel, and our complete solution then will be x minus c naught t plus this thing. Let us call this as equation number 6. So, then what does it mean? Let us go back to our figure here, when the membrane has completely bursted and two waves are set out in opposite direction. So, let us say based on this condition, what we, if we draw the profile x and this is your disturbance phi. So, here it is, and then based on this solution, if we put t is equal to 0, we again get back phi. So, this is really self consistent, but as the time propagates. So, right now we have x, we have phi, we have the general Gaussian pulse say at t is equal to 0, and so the wave splits apart. So, it comes down, becomes smaller at certain time, and then as the time evolves, it starts splitting into two parts. One, this pulse propagates in the positive direction, this pulse propagates in the negative direction. So, if this is of amplitude 1, say unity, so this will be 0.5. That is pretty easy to see from this slide, because you see here the wave actually has split into two parts, and you have basically you have two waves each of equal amplitude, which is half the amplitude of the original disturbance phi x. It is just that they are propagating in opposite direction. So, the end result, what happens for free waves that propagate in a duct in opposite directions, is basically under these conditions, when you rupture a membrane in a duct and you have no boundary conditions, that is nothing is coming back from here, nothing is coming back from here, only you are allowing only unidirectional propagation, no reflections allowed. Then you basically see the pulse being freely allowed to exit the domain into two equal halves propagating on opposite sides. So, this was for the general case when you have a general waveform, but 0 initial conditions. When we have a initial condition, of course, then of course we get what is called a D'Alembert solution. So, I will probably not go into too much detail in that, rather I will just note down the initial conditions when we something like P at x is equal to at generic x at t is equal to 0, say this is phi x as we had seen with respect to time. It is what? Instead of 0, let us say there is some function q x. So, these are our conditions. So, let us name this as number this as 7a, 7b. So, the idea is that if the initial condition, that is with respect to the time, derivative with respect to time, if that is non-zero, q x in general is non-zero, then what will happen? Is it still, how does the solution gets modified? So, here what we actually get is, I will write down the solution rather than working it out, which is left as a derivation for the students, half of phi x minus c naught t plus phi of x plus c naught t, and now what is the other term to incorporate this non-zero condition. So, to incorporate this q x condition, that is non-zero initial condition when you take the derivative of the pressure field at temporal derivative of the pressure field at t is equal to 0, what we get is the following. Maybe you can have a different choice of integrating variable, where this is from x naught minus c t and x naught or rather just so, clearly if q is 0, you get back the original solution. If q is non-zero, then what we probably have to do is that integrate, find out hopefully a closed form solution of this particular integral, put in the limits in terms of these variables. The physical significance is that we no longer have, even for a stationary medium, the medium is not moving. Note that in the duct that we had seen here, there is no flow, it is just a empty duct in which air is filled, a metal duct made of steel, brass, whatever, and you just rupturing a membrane. So, if you have a 0 initial conditions with respect to the temporal derivative, the resulting wave that you see here given by this solution, let us say number 8, you no longer have symmetrical waves, you actually have some kind of a bias. So, the waves will no longer have, will propagate with equal amplitude in both directions, they might be different depending upon how q y is. So, students can take up that problem, but the essence of this derivation of this example was that to show how free waves exist in a duct, and note that there are two solutions which you must carefully note, because you know this equation is a second order differential equation, second order hyperbolic equation. So, it has to have two solutions, two linearly independent solutions, the forward and the backward travelling wave. We will see in due course in the next few lectures or so that when we implement certain boundary conditions, especially when we enforce what is called the time harmonicity, we can get the wave equation actually become Helmholtz equation in the frequency domain, and then we can define your progressive wave, your standing waves, force solution and all those kind of things. So, we will take up those topics in the next few lectures, but for now what is important is to get to the derivation of how did we arrive at the second order differential equation which governs wave propagation, that is important. So, let us begin the derivation of the one dimensional acoustic wave equation that we had seen in the last lectures, a detailed derivation of that, because this will form the basis of the muffler acoustics, basis largely for the one dimension analysis of mufflers. So, let us consider in a fluid element, a small element, let us say a cylindrical element, something like this, and the mass, let us say we have certain mass that goes in this phase, which is x, let us say this is x and this is a small element x, delta x. So, this distance is x plus delta x, all right. And the density, let us clarify a few things. Density of the fluid, let us say this is air, is rho, and pressure is P. So, this P is different from the acoustic pressure, which we will name separately, and we will have a slightly different convention in terms of P tilde, we will get to that. So, P is the total pressure, and time of course is denoted by T, space is a one dimensional space. So, it is x, and other than that we have velocity, velocity of the fluid particles, that is u, let us say this is u, all right. So, one thing before we begin with the influx and outflux things that I am going to talk about, we are assuming here that the air particles here which are there everywhere, you know, it is a continua, although they are comprised of molecules, but we are considering the entire fluid element to be a part of a continua. So, that is why all these equations that we are going to present now will apply. So, the flux that enters this particular phase is given by rho, and let us say S is the cross sectional area. So, what is the total mass of the fluid that enters? So, before I begin this derivation, I must mention here that when we derive the wave equation, we first need to get to the continuity equation and then the momentum equation, and in addition to that we have equation for state, isentropic equation. So, all these equations they will be derived from the first principles and then linearized, because we are doing linear acoustics in this course, and then combined suitably, and finally we will arrive at that. So, the detailed derivation begins from what is meant, what is known as the continuity equation. So, what does the continuity equation do? It is an expression for the conservation of mass. So, whatever mass goes inside the phase say 1 and whatever mass that comes out of the phase 2, and what is the relation between the mass that goes into the system from phase 1, the one that goes out of the phase 2, what happens to the changes within this volume, that is within the entire volume, what are the temporal changes. So, we are going to see that the detailed derivation in this slide. So, I need to probably go back and forth. So, the mass that enters this phase 1 then is given by rho times cross sectional area u, notation x, and one that leaves the phase 2 is minus, because we are trying to understand how much mass is left in the system at time. So, if you have this amount of mass that enters within the system, the flux, and the one that goes out of the system. So, this is the net mass that is left inside the system, right, and what is that? There must be some time change of mass, is not it? Here you have density and surface area and then you have velocity. So, the mass that enters the phase 1 is given by rho s u at x, and the one that leaves the phase at 2 is also rho s u, but at x plus delta x. So, what happens is this is evaluated at x plus delta x, and so this is the total, this is the mass which is in flux, this is out flux. And what is the net, what happens to the difference? So, this is related to the temporal change within this volume, that is the orangish part that I have shown, the entire cylindrical volume. So, what is the volume of that? S into delta x, and density, if you multiply that by the density rho, that will give you the mass. So, temporal derivative of that is balanced to the net influx and outflux. So, this note that these changes are dynamic, they are happening both in space and time. There is constant influx of the mass from one side, constant outflux, and the difference of that will give you the temporal change of mass within that element. So, this is how we arrive at this one. So, now let us simplify this equation, and S is of course we are assuming here a constant or a uniform cross section area. And so, what we do essentially is rho u x minus rho u x plus delta x divide by delta x is equal to rho times, remember we are doing temporal derivative. So, in the limit that delta x is tending to 0, infinitesimal element, that is this element is getting smaller, delta x is smaller. So, what do we get? What we get, let me write this in this manner. This can be rewritten and then so this is your continuity equation. It basically relates the changes in density within the control volume, which is this one, and with the velocity of the fluid and with time and space. So, it basically tells you that del T of rho, that is temporal derivative of the density, plus the spatial derivative of the quantity rho u, that is 0. Here of course, I must mention that in the control volume here we are assuming that there is no sources, there is nothing that is pumping fluid. So, that is why you have put this thing 0. So, that is how you basically got this thing. Otherwise, suppose if there was a source, you would have put a term q or something like that with the same units as this one, which is your kg per second, but of course, we do not have that. So, I will strike off this part, and what we will probably go back to this one. So, before we end this lecture, I like to simplify equation 1 in the following form, which we will see will be useful in some other context. So, this equation, one dimensional equation for continuity equation, which is really an expression for conservation of mass. You also see in a lot of fluid mechanics text. So, we will stop here and then take on the momentum equation in the next lecture. Thanks.